Over the last few years, the demand for specialty coffee has skyrocketed. But as coffee houses pour more lattes and cappuccinos than ever before, baristas are running into an unexplained breakdown. Their milk is failing to foam. A perfectly poured, frothy dome will suddenly collapse and dissolve into a flat, watery liquid. To understand why this happens, we have to rethink the nature of milk. Rather than a simple, uniform liquid, it is a fragile, metastable emulsion. If you break down a single drop of milk, you'll find it's mostly water, about 87%. Suspended inside that water is a complex matrix of floating fat globules, dissolved lactose sugars, and dense protein chains. Because these distinct molecules are trapped together in one space, exposing that delicate matrix to heat kicks off a chaotic chain of physical and chemical reactions. Investigating the cause of this collapse requires a closer look at how basic heat alters milk's underlying chemistry. When temperature begins to rise, the first thing that happens is the fat globules melt. They spread out smoothly across the liquid, changing the texture and creating a richer feel on your tongue. At the same time, the heat breaks down the lactose into simpler sugars. This makes the warm milk taste sweeter to our palates. The most reactive components in this mixture are the proteins. Milk protein is comprised of about 80% casein and 20% whey. As the temperature climbs, these proteins react aggressively. The moment the liquid passes 60 degrees Celsius, those whey proteins denature. They physically unfold, migrate to the surface of the liquid, and link together. As they link up, they trap passing fat and casein molecules inside their structure. This creates a solid, rigid mesh, the skin that forms across the top of a heated pot of milk. That skin acts as a tightly sealed lid. As the water below turns to steam, the gas bubbles rise and get trapped beneath this heavy layer. The pressure mounts, the skin stretches, and seconds later, it ruptures, resulting in a classic kitchen boil-over. Heat forces milk's proteins to pivot from dissolved molecules to structural barriers that dictate the physical behavior of the liquid. But if you inject mechanical air and steam into the milk at a highly specific temperature window, between 60 and 68 degrees Celsius, those same unfolding proteins perform a different role. Instead of migrating to the top of the pot, the denaturing whey proteins rush directly to the surface of the injected air bubbles. They wrap around the gas, forming elastic, stabilizing cages. The melted fat globules then integrate right into the gaps of these protein cages. This fortifies the structure, creating a stable, velvety microfoam that bounces instead of popping. Building the perfect cappuccino foam requires a fragile, exact balance of protein integrity, a balance that is currently failing in modern coffee shops. To find out what is causing this foam failure, researchers at Clemson University designed a study to test the variables interfering with milk's chemical matrix. One significant factor researchers identified is the rise of organic milk. Lab tests revealed that certified organic milk produces a lower overall foam volume, and the foam it does produce dissipates much faster than conventional milk. The biological cause lies in the cow's diet. Organic dairy cows are fed a high-forage, grass-heavy diet, which provides less dietary energy than a conventional grain feed. Because the cow takes in less energy, it produces milk with a lower total protein content. Without enough whey protein available in the liquid, the milk lacks the building blocks to form strong, elastic cages around the air bubbles. A separate variable lies inside the dairy processing plant itself. Commercial facilities rely on clean-in-place systems. These are chemical cleaning routines designed to sanitize massive pipes and tanks without having to manually dismantle the equipment. The researchers wanted to know what happens if traces of those cleaners are left behind. They took test samples of milk, injected them with microscopic amounts of varying clean-in-place chemicals, dyed them pink, and frothed them with a commercial steam wand. Looking at this test sample, you can see how researchers visually measured the total height of the foam layer sitting on top of the liquid, logging both its initial volume and how quickly it collapsed. The findings were clear. If even a 1% trace of residual alkaline cleaner or defoaming agent makes it through the factory rinse cycle, it destroys the milk's surface tension. The liquid produces flat, soapy bubbles that pop almost instantly. This breakdown follows a logical path: protein structures weakened by foraging diets and compromised by residual cleaning chemicals. This failure reveals the high sensitivity of milk's chemical matrix. A single collapsed bubble in a coffee cup traces back to the specific type of grass a cow chewed in a pasture. It can also be dictated by the microscopic chemical washing routines inside a dairy factory miles away. Kitchen boilovers and perfect lattes serve as visible demonstrations of living chemistry. Milk is an environmental and biological record in a glass. To master it in the kitchen, you have to understand